Okay, so I'm going to be talking about my, my research program today. And basically, the idea is we're looking at materials using topology. And I'm going to describe to you several methods that I use to study materials and other complex physical structures from topology. So first, I'm going to start out with some examples to motivate this work. So up here at the top, we have, this is an aerogel. This is an exotic new material. It's quite poorly understood, but it has very interesting properties. For example, it's mostly air. So it's so light that if you take a bowl of air and you put it in the refrigerator for a little while, and you take it out, this will float on top of the bowl of cool air. Here we have an... I'm not sure how big it is in this picture, but I mean, you can see people like holding a chunk of it that's like this big. Yeah. Hmm? Yeah. Yeah.
It's used for detectors.
Okay.
I'm sorry, I have to tell them that why it's used for detectors. Because electrons in aerogel can move faster than the speed of light in aerogel. So they make shock. They make Cherenkov radiation, which is like shock. So they're very easy to detect. So energy electrons are easy to detect.
Okay. Okay, so here, here is an oxide glass, so silicon and oxygen. So this is a very common material. We have some in this room. But yet the methods to describe its properties in terms of its molecular structure are limited. Now we saw Yasu's talk a couple months ago that provided one way to characterize its properties. I'm going to describe a different way that captures some different properties of glass in terms of the topology. Over here we have, this is a three-dimensional network in R3, and I let this evolve the curvature minimization. This is a simulation I programmed, and it can be viewed as a very stripped-down model of a dislocation network. We'll be hearing more about that in a little bit. That's most of the computational results in the talk are about that. And here we have the foam on top of a beer, which is another disordered material, and I included that because I think even some of the more pure mathematicians would agree that that's a very interesting application to work on. Okay, so I'll talk about a couple more examples, and then we'll get on to the methods. Okay, so here we have an open cell foam, and I use this to motivate another one of the methods I'm talking about. So this is a very important material. It's used for catalyzing chemical reactions because of its large surface area and the fact that air flows through it. So for example, the catalytic converter in our automobiles is a platinum foam that catalyzes reactions that remove dangerous chemicals from exhaust. So there's surprisingly no good method to tell a priori why one open cell foam will be better than another for the purposes of catalyzing these chemical reactions. One idea the material scientists have is you want to construct a dual graph for this open cell foam and then solve the max flow problem with various weights for the edges. Now, the existence of such a dual graph is a topological question. While it's obvious in this case that a dual graph exists, it's not obvious that all open cell foams have a dual graph. And we say that if I get to it, it's related to the knottedness of the foam. And also, I think that if you have an open cell foam which is unknotted, I propose to use persistent homology to compute the dual network of this object. So I will get to that in a little bit. Okay, and so there's grain growth is another one. This is something my advisor Bob has been very interested in. I'm going to show you a movie of his last student, Menachem, in the back there. Okay, so here's Menachem's movie. So if this crashes, you can blame him and not me. All right, there we go. Okay, so here we have, so if you look inside a metal that's locally going to be crystalline, but you're going to have, it's not going to globally have all the same crystalline orientation. So there's going to be a two-dimensional network of boundaries between different crystallographic orientations. So you can kind of view this as as decomposing space into a union of polyhedra. And then as Menachem so greatly programmed, you can run a energy minimization on this and get an evolution process like this. Now, what I want, one of the methods I want to be introducing today is a way to test convergence of this process. Now, as you can see, all the grains are growing in size as time goes on. But the idea is if you look at properties that are scale invariant, then for any initial conditions you start this energy minimization process, they will eventually go to a steady state where these scale-free properties have converged. And I'm going to show you a metric that you can test such convergence with. Okay. Okay. So yeah, we want to. It appears that there's a steady state for which scale-free properties have converged, and we want to know dependence on initial conditions. So we need a metric, and I'm going to describe one based on the local topology. Okay. So these systems that I've shown you have interesting topology, but they have not yet been studied using topological methods. Now I have an asterisk there. I made these slides before I saw Yasu's talk a little while ago, and he had some very nice results with the persistent homology of oxide glasses. So I thought I should mention that. Also, I wanted to note that you can use crystallography to study. Crystallography captures the topology of ordered materials, but all the materials I showed you are disordered, and you cannot use it to study them. So the plan of my talk is first I'm going to introduce the method of swatches, which is a general method to quantify the topology of cell complexes. I will introduce a case study and talk about some computational results. That's the embedded graph that I showed you on the first slide. And then if I have more time, I will briefly describe two other topological methods, which are persistent homology, something some of you have heard a lot about, but from a slightly different angle, and the knotting of embedded graphs. Okay, so I'll start with the method of swatches. So the key idea of the method of swatches is you have an object called a cell complex, which I'll define for you in just a second. Examples, all the things on the first slide can be viewed as a cell complex in some way. For example, the grains in the grain growth I showed you, that's an example of a three-dimensional cell complex. And the idea is you quantify the local topology of these cell complexes using probability distributions of local configurations. Returning to the grain growth example, the material scientists might test convergence of the steady state by looking, for example, at the average number of sides of a grain. The idea of the method of swatches is to not just look at that, but so the number of sides of a grain is the number of neighbors of the grain. The idea is to not just look at that, but also to look at look at not just this one radius 1 neighborhood of a grain and its neighbors, but a grain and its neighbors and their neighbors, and a grain, its neighbors, their neighbors, and so on. That's the basic idea of the method of swatches. And using this, I define a distance on cell complexes, and this has many applications, for example, to quantify the variability of cell complexes or to compare experimental results with simulations. It's applicable to many physical systems and computable. And this is joint work with Jeremy Mason in Istanbul and my advisor, Bob McPherson. And paper is on the archive. Okay, so the method of swatches applies to regular cell complexes. So what is a regular cell complex? It's a space that's built inductively by attaching cells in each dimension via homeomorphisms from their boundaries to the existing structure. So if you know what a CW complex is, a regular cell complex is just the CW complex where all the attaching maps are homeomorphisms. So for example, here is a very simple example where we have 3 0 cells points, and then we glue 3 1 cells, these lines, and then 1 2 cell. The grain growth example is a 3-dimensional cell complex. We start with the vertices of the grains, then the edges, then the faces, and then the mass of the grains themselves is the 3 cell. Okay, so the reason we want to deal with regular cell complexes in particular is that we can describe their topology combinatorially. So we're going to use this to give a combinatorial description of the local topology of the cell complex. So by that I mean the properties of a regular cell complex, the topological properties, are fully captured by the adjacency graph of the cells. So what we do is we take the cells and we label them by dimension. So here the labels are in terms of the shapes. Over here, so the triangle is a 2-cell, the circle is a 0 cell, and the square is a 1 cell. And then we put an edge between cells of neighboring dimensions. Okay, so now we've represented our cell complex by a graph. And what we're going to do is we're going to look at local configurations in this cell complex. And we call that a swatch. The analogy is a swatch is a small piece of cloth that you use to study the properties of the whole cloth. So what is a swatch? The swatch is just the ball in, you select a 0 cell, and it's just the ball in the graph distance in the adjacency graph of a certain radius. So the graph distance gives every edge has length 1. So here's a one-dimensional cell complex here. So we count out both the edges and the vertices. So this is a swatch of radius 1, 2, 3, 4, 5, 6 at the 0 cell shown by the star. Okay, and so say, so the important thing about swatches is you can tell if they represent the same swatch type. And we say that they do if they represent the same topological configuration in our space. So that's the same as if we're looking at the adjacency graph world, that's the same as there's a graph isomorphism between them that preserves the labeling of the dimension. So yeah, two swatches are the same if they represent the same local topological configuration. We'll also need the, yes, up to homeomorphism. Yeah. So a subswatch, we'll need the definition. Subswatch of a swatch is just a swatch of smaller radius at the same root. So for example, and that you can only go out by radii. So if you just take these two here, that's not a subswatch. You go out by each radius. So for example, here you'll note that the subswatch of radius 2 is the same between these two swatches. Okay. Okay. Is there a question? Okay. So the idea is to look at the statistical local. Yes? Yes. You can capture different properties by doing that. For example, if you have a digon, this will pick up something additional in that case. Yeah. Yeah.
That's because you're looking at 3 coordinate classes, right? Go back to the picture.
Yeah.
No, forward. Yeah. I mean, this is special about the honeycomb. I mean, I think of it as a honeycomb lattice.
Mm-hmm.
This is special, the honeycomb lattice, the edges and the vertices.
I don't know what point you're getting. This works for, in general, any cell complex, including any one-dimensional cell complex.
Because I'm asking, if you suppose that you had things that had different 6-fold correlation, so that you thought you had a triangle,
Mm-hmm.
then would you get any extra information that also kind of the two sets of vertices are different.
Okay, I see what you mean. So in general, we're not looking at lattices with that because that's an ordered system.
I understand.
Yeah. I mean, there's many cases where the set of vertices and the set of edges will give you different information. If that's what you're asking. I'm not sure exactly what you're asking.
Okay.
Okay?
I'm not sure.
Okay. Okay. So the idea is we want to look at the statistical topology of a cell complex via these swatches. So we can't just take a look at a swatch at one vertex. We want to take a look at the swatch at all the 0 cells. So what we do is we look at each 0 cell of our cell complex. We fix a radius r, and we look at the topological configuration of radius r, the swatch of radius r at each 0 cell of our cell complex. And this gives us a probability distribution of local topological configurations, which we call the cloth of the cell complex. And so the cloth captures all local the family of probability distributions is the cloth. So you can let R vary and you'll get more and more information. And the cloth captures all local topological properties of the cell complex. And the idea is to then look at statistics on the cloth to compare different cell complexes. Okay. So one way we can visualize the cloth is via the tree of swatches. So swatches are themselves related by this graph, by the relationship of one being a subswatch of the other. So we can imagine growing out a swatch. And so this is the tree of swatches for with certain conditions added to the degree of the edges and the vertices. And so the cloth is going to be a probability distribution on each layer of the tree of swatches, subject to consistency conditions with the previous layer. Okay. Okay. So then the cloth provides a family of probability distributions which tell us about the local topology of our cell complex. So the idea is we're going to use this to define a distance on cell complexes. But before we can define a distance on cell complexes, we need a distance on swatches, a distance between local configurations. Okay, so we just chose a simple one, that the distance between two swatches is 1 over the number of cells of the largest common subswatch, or 0 if they are equal. So in this particular case, you can count out, and these have the same subswatch up to this radius here where you have the green squares. And so they differ if you go one more out. And if you count up the number of cells in that subswatch, you'll see that there are 13. So we said the distance between these two is 1 over 13. So this provides a way of saying how similar two local configurations are. And then we're going to take this and we're going to go to the whole cell complex. Mm-hmm.
Is that distance ever 0? What if you have the same thing?
Or 0 if they're equal. Yeah. Yeah. Okay. Okay. So now we have a distance on local configurations. So we have two cell complexes. We look at the probability distribution of local configurations in each. And then we define the distance at radius r between them. And we use a standard probability distribution distance called the earth mover's distance between the probability distributions at radius r. Okay, so the earth mover's distance is roughly the minimum amount of probability mass that must be transferred to transform one probability distribution into the other, where the movement of the mass is weighted by the similarity of the local configuration. Okay? And so this distance has many applications to compare different structures, to test convergence to the steady state, which is which I'm going to do in the case study, which I will show to you in just a second, or to perhaps iteratively modify structures to reach a desired state. Okay, so so we can talk about convergence of cell complexes using these systems in a more theoretical setting. So what we do is we define the limit distance as r goes to infinity. So in practice, this is going to stabilize at some point, unless you're dealing with infinite systems, as the limit as r goes to infinity of dr of C1, C2. And we say that suppose we have a sequence of cell complexes. We look at their probability distributions of local configurations, and we say it converges if it is a Cauchy sequence in the distance d. And note that if the sequence of cell complexes converges, that is equivalent to all Swatch frequencies converging. The probability of any local configuration inside these cell complexes converges. And we can connect this to the theory of Benyamini-Schramm graph limits. And a corollary of that theory tells us that if we have a convergent sequence of cell complexes in this distance d, that gives rise to a limit distribution on the space of all countable connected cell complexes with a root specified. And furthermore, this distance can be extended to the space of these distributions. So talking about the convergence of a sequence of cell complexes to a probability distribution makes sense. And I hope to connect this to notions of universality coming up in physics and material science. OK. And this convergence also implies that all local topological properties converge. All those that can be defined in terms of maps from a fixed graph into all of the cell complexes CI. So for example, if you have grain growth, the number of grains with 5 neighbors is an example of a local topological property. So if we have a sequence in grain growth that converges in this sense, then we know that that property converges. And if you want to know more about the theory, I recommend the book Large Networks and Graph Limits by Lovash. OK, so on to some computational results. OK, before I go on to the computational results, are there any questions about the method of swatches? People good? OK. Large Networks and Graph Limits by Lovash. So I believe the last 3 or 4 chapters are about Benjamini-Schramm graph limits. OK, and did you have a question?
So you only keep track of the ones that
No. So you have a 3-dimensional cell complex, or a 2-dimensional cell complex, for example. You represent it by the adjacency graph, which you can view as kind of a 1-dimensional object. Yeah. OK? But the computational example is a 1-dimensional example. But this can be used for a regular cell complex of any dimension. OK. So I'm going to tell you next about a case study, and I'm going to use the method of swatches to study it. OK, so the idea is to simulate the curvature-driven evolution of a 1-dimensional network in 3 space, an embedded graph. Then we're going to represent this network as a 1-dimensional cell complex with vertices and edges. We're going to compute the cloth. We're going to compute the probability distribution of local configurations for a radius less than 10. And what we're going to do is we're going to try to test the steady state hypothesis in this case. We're going to find a candidate steady state. And we're going to show that if we take the distance dr to this, regardless of the initial conditions, it converges to this steady state in the distance dr. And then I will also discuss other applications of topology to this case study. OK, so the model is a curvature-driven evolution of polygonal curves in the 3 torus, because we can't simulate all of our 3. And the polygonal curves meet each other at vertices of degree 3. Just some language. And we evolve it by energy minimization, assuming a constant energy gamma per unit length. So this can be viewed as a very simple model of a dislocation network in the process of recovery. So let me show you a movie of that now, so you can get a sense of what's going on. Tried to embed it in the slideshow, but that just causes it to crash. OK, so here we have an embedded graph. And it's evolving by energy minimization. And note all the vertices have degree 3. And as time goes on, the edges become longer. And you'll also note that there are some topological moves occurring in there if you look really closely. Like there's a polygon shrinking to a point. And there's a couple other types of topological moves in there, which I'll tell you about in just a second. So any question about this model? Yes, this is on a torus. If you look hard enough, you'll see that what goes out one side comes in the other side. Well, the energy, it's just we have a constant energy per unit length. So that in turn, there are several ways to compute this in practice. One way is you can just take the length of an edge and you assign the energy, and then so these are discretized. So you have a polygonal curve, and at each point along the polygonal curve, you associate to it half of the neighboring segments, and then you can do it that way, or you can view it as an example of a curvature flow. And then you can use certain discrete notions of curvature. And so there are several ways to implement this, and it turns out using the method of swatches, you can show that it doesn't really matter what you do. Same behavior. Yeah? What do you mean? It's just that it's in the 3 torus. Yes, that's a very good question. They do intersect. Not for these initial conditions, but for other initial conditions, which are chosen so that they intersect. And the question of what should happen when they intersect is an interesting question, and I'll get to that. Yeah.
Are the computations reasonable?
Oh, yeah, very much so. Except, I mean, it gets a little harder if you start having to detect the intersection of edges. But even so, I've been able to run very large systems.
Yeah, it's all local.
Yeah, it's all local. So yeah, it's not a realistic model of a dislocation network where you have other longer range interactions. Yeah. Okay. So let's apply the method of swatches to the test case. So first, to finish the description of the model, I have to explain the topological moves that occur. So you can have an edge shrinking to a point, in which case we flip the edge. And since we're in 3 dimensions, there isn't a unique way to do that. So we just make a smart choice that has to do with the angles on either side of the edge that's shrinking to a point. And the other topological move is we have a diagon shrinking to a line. So we just go here, and then we merge the 2 edges. And if you look closely in the movie, you'll see there are a number of cases where a polygon is shrinking to a point. But you can express that topological move as a composition of these 2 topological moves. So in the model, there's no need to have specific things for larger polygons than the diagon. And as Menachem pointed out, since we are in 3 dimensions, we sometimes have this case where 2 unrelated edges are going to intersect like this. Now, I tried two different topological moves when this occurs. One is you can just ignore it, and then you can run much larger systems. And the other is when you have 2 edges that meet like this, you add a 3rd edge between them. You form a new edge. And it turns out that using the method of swatches, you can show that for the long-term steady state, the choice of topological move here does not matter. You get the same steady state. And I'll explain that more later. OK. And to run the simulation, we need initial conditions. So the one I showed you was a 1 skeleton of a Voronoi decomposition, or a slightly modified one. So the Voronoi tessellation is you put random points in the 3 torus, and then you get a cellular decomposition of the 3 torus by associating to each of our random points all the points closer to it than to any other point. So that means you write the 3 torus as a union of polyhedra. And then you take, to run this simulation on it, we take the 1 skeleton of that. Now, the 1 skeleton of that is actually going to have degree 4 at each vertex. So that's not what we want. So what we do is instead push it off just a tiny little bit, and then let it evolve. And then I designed another initial condition just to look designed to look very different than this, which is, it's designed actually to have a lot of the intersection move that I described earlier, which the Voronoi has very little of. And this is just, you put a lot of random points in 3 torus, and you match them up randomly as long as their distance is below a certain threshold. And using the method of swatches, we can show that under this curvature flow, they both evolve to the same steady state condition, which kind of looks like this, which does look like this. OK. So now we've defined our case study. Any questions about the case study before I get on to the computational results? OK. So we're going to use the method of swatches to study this. So first step is to simulate the curvature revolution of an embedded graph in 3 torus. We're going to represent that as a 1-dimensional cell complex. We compute the quath. We compute the probability distribution of local topological configurations for a radius r less than 10. And then what we do is we find a candidate steady state for which many properties appear to have converged. So I just took my largest simulation. I looked at several properties, found one that looked like they had converged. And now I'm going to use this more more general, less ad hoc method to test the convergence using the distance dr. Okay, so let's look at some examples. Okay, so here is an example of the system evolving through time. So we have time steps here. So run starts here, and we track the distance to the test case. And as time goes on, the distance decreases very quickly to this level here. This is the distance to the test case, and then it stabilizes for a long time. And if I let it go out any further, you'd see it blows up here when it gets too small because of both the boundary conditions and finite size effects. And also, you'll see that it's not quite 0 here, but I'll explain that in terms of finite size effects in just a little bit. Okay, so we're looking at the distance to the test case as the system evolves. Now, a problem is the time steps isn't really a universal system of measure. Some initial conditions may evolve more rapidly than others. So what we're going to do is we're going to change the coordinates so we can compare different systems. What we're going to do is instead we're going to look at the number of edges versus distance to the test case. So this is a little confusing. I reverse the direction in which it converges because generally the number of edges is going to decrease. In this particular case, it actually, so we start here. And so this is random graph initial conditions, which has a lot of intersections. So what we're doing is we're adding edges a lot at the beginning because there's lots of these intersections. So the number of edges increases and then decreases as it converges to the steady state here and then blows up towards 0. Okay, so this is a way of parameterizing the evolution of our system so we can compare different systems. So yeah, it goes down like that. So now we can compare this evolution with that of different initial conditions. Okay, just put it on a bigger graph so we can have this one here. So we have a large Voronoi, and we have number of edges versus distance to the test case. So okay, so this doesn't provide much information. So let's put that on a log-log plot just a second. So we have a very large Voronoi initial condition here. And as you can see, it also goes down very fast. And then there's this little bump. I'm not sure yet what's going on there. And then it also is close to the test case for a long period of time, as is this one. But the other examples we're going to look at are going to be on the same order of magnitude as this one. So I'm just going to put it back in the other coordinates. OK, so yeah. So here, that's just the plot I showed you before, number of edges versus distance to the test case, where the beginning is just way far off to the right. OK, so to show that we're not getting something trivial here, so here's a smaller Voronoi initial condition. And as you can see, the distance to the test case does decrease very rapidly at the beginning. But with this size of initial conditions, there's a bigger gap between it and the test case. Yes, it does. For the Voronoi, they generally have that dip. And I'm not sure exactly what's going on.
So what would the dip be or watching?
That the
It would mess it up. It would be very close to everything, and then it starts not being close.
Yeah, that's so the method of swatches as of yet only includes topological information. So what I think is going on is there's some metric information that hasn't quite converged at that point, and that causes it to it doesn't stay there, and then it moves away a little bit, and then it comes back. Mm-hmm.
What we don't see here is the time limit. Does it go very slowly for that dip or very quickly for that dip?
I don't have here. I think it goes quite quickly, but I don't have the graph here to show you. Yeah. Okay. And yeah, this one does not have the dip, as you say. Okay. All right. So also we can look at so that actually you can see here that that's somehow an artifact of the Voronoi initial conditions, because here we have these are both the random graph initial conditions, and this is one where at the intersection we add an edge between them. That's why the number of edges increases at first. And here we can look at the same thing where we just let the edges pass through each other. And in both cases, they go down quickly to the steady state, but there is no bounce. So that has something to do with the Voronoi. I'm not sure exactly what it is. But the important point to see here is so we have two with random graph initial conditions with different topological moves. Their behavior at the beginning is a bit different, but toward the end, they end up in the same spot. OK. And the reason for that is we can take a look at so we're going to take a look at this one, the curved one with a lot of intersections. We're going to see what happens as the system evolves. And the reason why the intersections don't matter in the end is all the intersections happen at the beginning. So basically, you have relatively long, at the beginning, you have relatively long edges with respect to the size of the system. And those all intersect with each other, and they break up into smaller edges that will no longer intersect, is basically what's going on. So here is the preponderance of topological moves that are intersections. Starts at about 50% at the beginning. And then it declines rapidly until it's down to basically 0. Yeah. Yeah.
Somehow know that they no longer intersect. Sounds like a guess.
Hmm? Sounds like a?
Yes. They go through once.
Mm-hmm.
But they never come back.
They don't come back, no. Hmm?
To me, that sounds like a guess, but it's a theorem.
Oh, it's not a theorem. These are computational results. Yeah, that they don't come back.
You keep track of them somehow?
Yes, you keep track of them through the computation. That's what this graph is. Yeah. Yeah, you have to keep track of them in order to implement the topological move. Yes, it would. Yes, it would. Now, it's hard to prove much of anything about these systems of curvature flow with singularities, yeah, unfortunately. OK, so a bonus of this is if we just care about the steady state statistics. Mm-hmm. You were going to say something? See, detecting the intersections is computationally expensive. So a bonus of this is if we just want to study the steady state statistics, we can run a simulation without detecting intersections and get the same information. So we can get much larger data. Hmm? Oh, at the very end? You mean here? Where it's going back and forth like this? This is just because the reason it starts varying like this is our system's getting smaller, so there's a lot of statistical noise here. So you can see it's both up here and down here. And this one's both up here and down here. It's just we're looking at a system with very few edges. And so you have, there's not many topological changes. So that means that if you look at the probability distribution of the topological changes, it's going to start to bounce around a lot. So this isn't just one time here. This is a bunch of stuff all compressed together. So there's one area where, I don't know, there's only one edge flip in the amount of time. Basically, the way I got this graph is you split up it into intervals depending on the number of edges, and you measure the number of topological moves that occurs within each interval. So if the interval has only one topological move and it's an edge flip at the end, it's going to be 100%. OK? OK. So as you can see in the graph here, the distance to the test case goes down to 0, but it doesn't appear to actually be 0. So there's a question of, is this finite size effects, or is this something real? So now we're going to have a way to test that.
Do you know why it goes away from that? At the very end, it always goes away from that.
Well, this partially explains it. This partially explains it here, which is we want, so so the cloth is a family of probability distributions. You fix a radius. This is a probability distribution of local configurations. And this is a pretty complicated probability distribution because it's highly, different swatch frequencies are highly correlated. For example, if you look at a swatch of radius 10 at one zero cell, and you look at the zero cells nearest to it, they're going to be determined up to quite a high radius. So it's hard to do a priori statistical testing on this. But instead, what we can do to test finite size effects is we have a test case here. And the test case is really big. So the idea is to compare the simulation with a subsample of the test case that's about the same size, where the subsample is chosen carefully in order to capture these complicated properties of the probability distribution. And we say that the system has converged to the state represented by the test case if it is statistically indistinguishable from a subsample of it. So here what I've done is, so we have a very large test case. I think it's about 5 million edges. And what we do is, this is 50,000. So this is relatively small compared to 5 million. So we can take a bunch of subsamples with 50,000 edges of the big test case. And then we can see what's the variability in the cloth statistics at radius r equals 7 for these. And then we can plot a bar which is within 1 standard deviation of it. So each bar is 2 standard deviations long. And we can see how that compares to our simulation, which is from a different simulation. And you can see here that for the large Voronoi, you're inside this bar for a long time. And for the random graph initial conditions, you're outside it for a little bit, and then you enter it for a while. And for the smaller Voronoi, you're outside of it here, and then maybe you're in it here, and then perhaps you leave. OK, so generally for Voronoi initial conditions, you find that the number of edges has to decrease by a factor of 10 from what you start with in order to get to this steady state. So Constantine, part of the blow up is explained here, and that is just the finite size effect grows very quickly as the size of your graph decreases, or the size of your cell complex in general decreases. And there's also some additional, that doesn't explain all of it. Some of it has to do with the fact that that there are boundary conditions for the simulation. We're simulating on the 3 torus. So at some point, the boundary conditions start to affect it, and it doesn't behave like the system should behave. Instead, it starts seeing the other edge of the torus. Yeah. So that's why it blows up at 0. OK. OK, before I go, OK, how much time do I have? I have 15 minutes. Before I go on, I'll discuss briefly applications of other topological methods to the study of materials. Before that, does anyone have questions about the method of swatches or the application to this? It's quite complicated. It's very hard to get estimates of it. For example, I tried for a little while to see, I don't know, so say you're looking at a specific case where you're dealing with, like this, each edge is adjacent to 2 vertices, and each vertex is next to 3 edges. And you want to ask, what are the asymptotics on the number of possible swatch types as the radius goes up? And it's very hard to estimate that, but it appears to be at least exponential. So it's quite a complicated space.
Wouldn't it be at least as bad as looking at stars of vertices in a cell complex? Because that's what it seems to be doing. How many different types of
Mm-hmm.
You're just doing how many.
I'm just trying to think of it how long you expect.
Oh, so there is a topology on this space, a very nice topology which agrees with the distance, which is what you do is, so what is it? You're looking at the space of all swatches. So that's going to be a rooted, countable, connected graph. So you look at the space of all rooted, countable, connected graphs, and you have to look at them with below a fixed degree. That's important. You need to fix the degree bound. And then you can look at this space, and you can define a topology on it by your open sets being the extensions of a given swatch type. I.e., you fix a swatch type, and then you look at all larger swatch types that have that as the subswatch of that radius. And that gives a topology on this space. Now, it's a very complicated space, but that's one way you can look at it.
So, just to check, and
you gave a metric for that.
Yes, that's a metric. Yes, it does. Yes.
So these patterns now, is that a nice computer
Mm-hmm.
when you make your complex
Mm-hmm.
and you map into that space, and now you're evolving that nice continuous process on that space?
OK, so let's think about this topology for a second. It should be, so the topology is, so your open set is the extensions of So when you have a topological change, I believe that's not going to be continuous. Yes, the jump is very small. And if you're thinking about, like, really for the theory, you should be thinking about an infinite system, in which case you could imagine continuous transformations on the space. But yes, in practice, these computational jumps are not going to be continuous, but they're going to be quite small if your system is large. Okay? Any other questions before I go on to, I guess, persistent homology and knotting? Okay. So you can also use persistent homology to study these things. And the idea is to try to use it to find voids in a material. So coming back to the open cell foam I introduced at the beginning, the idea here is we want to compute a dual graph to study its properties. And the way I propose to do that is we're going to try to, it looks here like this is the one skeleton of a three-dimensional cell complex. And you want to try to recover the three-dimensional cell complex using persistent homology. So the idea is to take this space and expand it. And as you look at the epsilon neighborhoods, and as epsilon increases, holes form and disappear. And you hope that in the case you're working on, each hole is going to correspond to a cell of the open cell foam. And then using that, you can take a look at the adjacency of these cells, and that will give you a dual graph. OK. So to give you a better sense of what's going on with persistent homology, there's a couple figures in Mathematica. All right, I'll just look at one. The idea is we're looking to find voids in a material. And so, yeah, so you have, this is the steady state from the simulation I just told you about. And the idea is that we're going to expand it to try to find voids in it. So here, for example, we have one subset of that steady state. And the idea of persistent homology is you take epsilon neighbors of it. You expand it like this. And in this case, you're going to get a hole forming in the middle, representing a void in this embedded graph. And I guess we're not seeing the whole thing here. Is that, yeah, I'm sure almost all of you have seen these plots before where we can represent the form, the appearance and disappearance of these voids by a scatter plot, where the void forms at a certain point, and then that's the this is not showing up, and that's the birth axis down here, and then it dies at a certain point, and that's the death axis over on the y-axis there. Okay. So the idea is to look at a complex geometric structure and to use this plot to study the number of voids in it. So this is just the second-dimensional persistent homology. There are other dimensions of persistent homology, and I don't have time to discuss them here, but I see them also having applications. Okay. Okay, so the philosophy is instead of is to use persistent homology to study the geometry of a fixed object. So this is different than what you may have seen from Carlson, where he uses it to try to detect topology in a noisy, from noisy data. Here, our randomness is in the object itself rather than sampling from the object. And the topology actually reflects the shape of the object rather than being the topology of what we're sampling from. And so this philosophy was introduced in my paper with Bob, Measuring Shape with Topology. And here we say that if we have our embedded graph, we say that holes in x epsilon correspond to voids in x. So then the second dimensional persistent homology of an embedded graph in 3 space corresponds to voids in the space of that embedded graph. And the idea is to find voids in materials. OK. So what we can do is we can plot the time when a hole forms versus the time it disappears. And this gives us a scatter plot which describes the properties of the voids in the material. And the points on the x equals y are noise having to do with how we sampled the space. Yeah. OK. So we can take a look at the one skeleton of a Voronoi decomposition. And we could try to, so that's a one-dimensional cell complex. That's the skeleton of a 3-dimensional cell complex by definition. And you can see here that we recover the 3-dimensional cell complex structure. Or rather, we haven't recovered the structure yet. We've recovered the cells. recovering the structure is something I'm working on now. So actually, the Voronoi is actually a bit larger than the one pictured here, and it had, if you count up the number of points above the diagonal here, and you count up the number of points in the Voronoi, you end up getting the same number. So that isn't too surprising, but it's good confirmation. Now, what I found quite surprising is if you take a look at this steady state of this curvature-driven evolution process. So this is not something you would expect to have voids in it, and yet it has voids on the same size scale as the Voronoi with the same number of edges. And yeah, you can see this is the plot for this one and this one, and you can see, well, the picture is of different size scales, but the systems are of the same scale in terms of the number of edges. And you can see that if you look at the dots, they're the same size. So even though, like, you might look at this and not see voids, they are there. And that was quite surprising. So then I said to myself, I want to try to see these voids. So I developed some code to visualize minimal representative cycles of the persistent homology. So here is one here. Can people see this well? I can also rotate it around. That provides a better view. I'll rotate it around. Yeah, it's a little hard to see on just two-dimensional projection. But so here, you can rotate this around, and you can see that this red outline is actually the outline of a void that was detected using persistent homology. OK, is that clearer now? OK. OK. There you go. Yeah, you can see that there's a void in there. OK. So one thing that, OK, so what I did was I created a way to compute minimal cycles. So if we're thinking about persistence in this geometric way, something that came up is that persistent homology does not, the way, so so if we're looking at the second dimensional persistent homology of something in R3, we're looking at holes in the complement of our space. And it turns out that those can form in two different ways if we're looking at something in R3. They can form from a splitting event, such as the one we have here, is if we expand this void here is going to split into two voids. Or you can have an event where a hole in the complement is created. A hole in the complement of our space is created out of the component of R3 containing infinity. And those geometrically are quite different events. But persistent homology ignores the difference between two events. And in fact, using just the persistent homology intervals, or the scatter plot of the persistent homology, it's going to give you a new point when this splits off. And it's not going to tell you that it's related to this other point. So based on that, I think that the correct structure in this case is not a set of intervals or a set of points, but a tree, where if you have a splitting event, you have a split in the tree. So I just implemented an algorithm that, for my particular case, computes this tree. And also, I'm not sure, it appears to be very difficult, and it might be impossible to define it for cases, for example, the first dimensional persistent homology of something in R3. So that's something I'm thinking about. And another thing that this brings up is, say we have our open cell foam. We want to compute its dual graph. If we find the pH2 tree of it, that will tell us something about the adjacency of the cells in it. But it won't tell us everything. So I'm also working on ways to compute adjacency of minimal cycles to have even more geometric information added to the persistent homology. OK, so I'm at time, so let me go to my conclusion. So interesting topology.
Tell us about the knots.
Tell you about the knots?
We'll do it very fast.
OK. OK. So many embedded graphs from physical systems appear to be unknotted, and we want to try to find a way to measure it. So one idea, which actually recently I'm pretty sure that this gives a different answer than the definition, but I mean this is all very preliminary work, is what we do is, OK, it's hard. I'll make a point in a second that it's hard to define the knottedness of an embedded graph. So one idea is you take a look at your embedded graph, and you take a look at each edge in your embedded graph. You look at the shortest loop containing that, and you ask, is it knotted or not? And yeah, so then you can run my simulation, and you can track the number of knots in the simulation. So if you start with initial conditions that are knotted, which the random graph initial conditions, they're the very messy ones that gives you lots of intersections. Those are quite knotted at the beginning. But very quickly, if you run the curvature flow on it, the number of knots in these shortest cycles decreases very, very fast.
You mean lengths? What do you mean? Look at the shortest curve and
Yes.
itself.
Yes. I'll get to that, and I'll get to something related to where you're headed in a second. Yeah, you ask if it's a knot with itself. And there's different ways of defining the shortest cycle. So you can define it in the graph distance, which is the blue, or the embedded distance, which is the green. And in both cases, the number of knots in these shortest cycles decreases very fast. Yeah, so then, yeah, curvature-driven evolution appears to unknot networks. And then, oh yeah, this was the simulation with the intersections. You can imagine there would be a relationship between the intersections, the behavior with the intersections and the knottedness. So if you, instead of forming a new edge at the intersection, you just let them pass through freely, the number of knots decreases even faster. And say something more about that? OK. So then the question is, in general, how do you define an unknotted embedded graph? And it turns out that this is actually a hard definition to make. For example, if you take a look at the standard square lattice here, it's going to contain many, many knots. But I mean, I think for a reasonable definition, you wouldn't want this to be knotted. So there's several definitions in the literature. But Bob and I have our own, which is, and this is very preliminary, that an embedded graph is unknotted if its complement has the homotopy type of a graph. Now, I'm pretty sure I can't recall the example off the top of my head, but I think a couple weeks ago, I was looking at an example where it is what? It's unknotted, but every shortest cycle is knotted, or something like that. I need to think about that a little more. This is where I'm just starting to work on this.
So the homotopy type of the graph, is that just a wedge of sphere in the circle?
Yeah. So yeah, that's one way that you might think to try to test it using the fundamental group. So there's a theorem that I'm thinking about with regard to that. But that's for the future. And I'm running out of time, so I'll just OK. So and I also want to note that this definition of knottedness is equivalent to the existence of a dual network. So if you have an unknotted graph, its complement has the homotopy type of a graph. So you can construct this graph, yeah, this dual graph. And I'm working on several theoretical questions surrounding it. And oh yeah, there's your question about the wedge of circles. Is this equivalent to pi1 of the complement being free? Yeah. OK. Oh, and that's a knotted material. This is it's a metal organic framework. You probably know a bit more about this than I do, I'm guessing.
No, I've never seen it before.
OK.
What are those things? They look like kidney stones.
I'm not an expert on this. So I just tried. I wanted to find a picture of a material that had knots in it, and this is one. So I'm just going to say that they may have interesting, useful properties. So just not just the property of unknottedness is useful, but the property of knottedness is useful as well.
Oh yeah. I'll show you something.
OK, so you should thank me for not including pictures of kidney stones in my talk. OK, so in conclusion, there's many examples of interesting topology in material science and physics. And topology could be useful for understanding systems that are currently not well understood. And this is just beginning, so there's a lot of things to work on. And finally, perhaps the study of these applications will provide new ideas for topology.